Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to the 7th lecture of the course Fracture, Fatigue and Failure of Materials. So in today's lecture we will be talking about fracture toughness and plane stress, plane strain condition. So two very major concepts of fracture mechanics will be discussed starting from today, and the basic concepts that will be covered in this lecture are the following. First of all, fracture toughness. So far we have discussed about fracture strength and how this can be generated based on Griffith criterion as well as their modification. In this class, we will see that what is the difference between fracture strength and fracture toughness, what exactly is fracture toughness and why is it so important in case of fracture mechanics. Following this, we will also look into the different geometric factor that can lead to modification in the fracture toughness of a material. And further to that, we will discuss about the linear elastic fracture mechanics and the hypothesis associated with that. And finally, we will introduce the concept of plane strain and plane stress. So let's see what we have seen in the last lecture is about stress intensity factor, and we have seen that if there is a crack present in a material, something like this, at any point away from the crack tip which is at a distance r and at an angle theta, we are able to find out the stress scenario at any point away from the crack tip, and this is given by particularly this factor here denoted by capital K or the stress intensity factor. This is essentially a function of the applied stress, crack length as well as a geometric factor, and it is considered as y sigma root over pi a. So that is how stress intensity factor is generated at any point. And interestingly, the critical value of this K or the stress intensity factor at which fracture happens, that particular value is known as the fracture toughness. So fracture toughness is nothing but the critical value of K, typically denoted as Kc. C stands for critical or K1C. Okay, this 1 comes from the mode 1 loading condition. So this is not I, this is just 1, capital Roman 1, and C, as I said, stands for critical, right? Since most of the fracture toughness tests are pursued in the mode 1 loading condition, that's why K1C is very much commonly used as a term to determine or to denote fracture toughness. Now, at certain point, this critical value of K at which fracture will occur, that is a fixed one. So whenever such value is reached, there will be fracture, a fracture will materialize. So that is how K is very, very important, or Kc is actually very important. And if we know the fracture toughness value of a material, we can determine that when the fracture will occur, or if we can increase the stress further so that there will be still no fracture. So if we use this relation here, so K is given by y sigma root over pi a at the point of fracture when K turns to Kc or K1C, at that point we actually have the relation as y sigma. Now sigma at the point of fracture will be denoted as sigma f, which is nothing but the fracture strength of a material, and A at such condition at the point of fracture will be the critical value of crack length or denoted as AC. Okay. So if we are knowledgeable about the fracture toughness of a material, we can also in turn determine the fracture strength of the material or the critical crack length, or vice versa. If we are knowledgeable about the fracture strength of a material and the critical crack length, we should be able to figure out the fracture toughness of a material. Now, information about the fracture toughness is very important when we are thinking of using this for certain application. For example, at the service condition, if we know that fracture toughness of, let us say, titanium alloy, which is used for aerospace application, if we know the fracture toughness of that particular alloy, we should be able to figure out either of these two, either the maximum fracture strength that it can survive, or maybe the critical crack length that survive the condition till there will be any fracture. Okay. So, this information is very helpful while designing something based on the material's properties. So, depending upon the service condition, the maximum allowable stress limit or the defect size can be determined, and then we can predict that whether fracture will occur or not. Okay. Now, if we try to draw the analogy between the different parameters that we have discussed so far, small k, capital K, or the critical value of capital K. Now, small k is nothing but the stress concentration factor. If we can look into our previous lectures, we will see that if there is a crack of half length A and radius of curvature for the crack tip is rho, then small k, or the stress concentration factor, this is given by root over A by rho. On the other hand, if we are talking about the stress value or the stress scenario, the energy at any point away from the crack tip, which is at a distance r at an angle theta, then that will be given by the capital K, or the stress intensity factor, and that we have seen is related to y sigma root over pi a. Okay. At the critical value of K, fracture will occur, and then it will be the fracture toughness of the material. So, not all the values of K are fracture toughness, but the critical value of K can only be termed as fracture toughness of a material. Now, at the first point, if we try to draw the analogy between Kc and K, we can think of this as the same as the difference between strength and stress. So, if we look into the stress strain diagram, the typical stress strain diagram of a material, let us say a metallic material, this is what we get. Stress values varies with strain initially as a linear way. So, this is as per Hooke's law, and we get the elastic modulus. At every point of strain, we get the corresponding value of stress, but at certain point, when the deformation mode changes and there is the onset of plastic deformation, that particular point is known as the yield strength of the material. Similarly, the maximum value of this is termed as the ultimate tensile strength of the material. So, that is also a stress value, but that critical values are termed as strength, either yield strength or ultimate tensile strength. In case of fatigue, that can be termed as fatigue strength or fracture strength. So, at that critical value of stress, when the deformation mode changes, that is known as strength. Similarly, the critical value of K at which fracture occurs, that is known as Kc, or the fracture toughness. So, that is the basic analogy between Kc and K, same as strength to stress. On the other hand, if we try to find out the difference between small k and capital K, small k, it is sometimes denoted as Kt with the subscript T denoting the stress concentration factor, or simply small k as the stress concentration factor. And the basic differences between these two are as follows. The capital K, or the stress intensity factor, includes not only the stress level, but the geometric factors both taken together. So, it includes the stress level, and as a result it gives us a wholesome picture in front of the crack tip. Okay, at any point away from the crack tip, if we know just the crack length as well as the applied stress, we can figure out the critical or the value of K, capital K, stress intensity factor. On the other hand, small k, or stress concentration factor, is particularly related to the geometric factors and not the stress level, the applied stress level. Okay. So, this in that sense is a kind of conservative one, the small k one, because it does not include the applied stress levels, and so we cannot predict that what or how it will behave in case of the service when we know that there is certain stress limit that we need to apply. We cannot figure that out from the small k or the stress concentration factor, rather stress intensity factor gives us a clear picture. Also, the unit of stress intensity factor, which is related to, so let me just write here, unit for K is related to the unit of sigma, which is MPa, and A, which is meter. Okay. So, the unit is MPa root meter. On the other hand, the unit for stress concentration factor is just 2 root over A by rho. So, the unit of A is also in millimeter, unit of rho is also in millimeter. So, basically that cancels out, right. So, it is an unitless parameter. So, that is also another difference between capital K and small k. So, now that we know about the difference and what exactly is fracture toughness, and for the case of fracture mechanics, or most importantly if we try to involve this fracture mechanics, include this into failure analysis, because our target is to find out that how long a material or a component or a structure can survive and what can we do to enhance the life of this material. So, we always try to control these parameters, right, so that we can change or modify the values of fracture toughness or strength in a way that we can achieve higher and higher or better and better performances, right. And in that way this factor here y, which is what we have not talked much about. So, this y has a very leading role to play to control the fracture toughness of the material. We have seen that how the value of y changes if we are changing the configuration of the crack and as well as the position of the crack. Y is particularly dependent on 2a by w, right, where a is the crack length and w is the width of the component. So, if we are changing this, then y is also changing. So, that means that the component size as well as the crack length is the most important factors which changes the value of K, the stress intensity factor, and then we can be able to delay or maybe pronounce the fracture behavior or the fracture occurrence if we are varying the parameter y. Okay. So, the fracture toughness, as I said, is the critical stress intensity factor at which fracture occurs, and for the case of an edge crack thing, we already have seen that in this case y is nothing but 1.12, and this is valid only when 2a by w is much less than 0.1, or in other words, in the very basic meaning of this is that the crack length is very small compared to the total width of the component. Okay, so, this is the width of the component, and in that case K1C is given by 1.12 sigma f root over pi AC at the point of fracture. Okay. So, for the case of center crack, on the other hand, we see that the crack length or half crack length here is A, and the total width in this case is W. So, that leads us to y equals to 1 again for this condition that 2a by w is much less than 0.1, and as a result what we get is K1C equals to sigma f root over pi AC. So, this is nothing but what we have seen for the case of Griffith criterion. If you see that this is exactly what we have seen for the case of Griffith criterion. So, K is nothing but this parameter here, sigma f root over pi A, and that is a materials property. That is what Griffith has determined, which is valid only if we have a center crack through the thickness crack and the crack length, total crack length is much smaller compared to the width of the component. Okay. So, based on this understanding, let us solve a problem so that the concept gets more clear. What it says is that a stress of 1000 MPa is applied to a 1 inch wide 4340, that is a grade of steel component having a surface crack of length 0.5 millimeter. Okay. So, that means that sigma A here is 1000 MPa and we have a surface crack. So, that means an edge crack, and of course, for that y value should be 1.12 and A is given by 0.5 into 10 to the power of minus 3 meter, since we need to consider everything in the unit of meter for length and MPa for the case of stress. Okay. Now, considering the material's fracture toughness as 55 MPa root meter, determine whether the component can survive at the applied load. So, we need to figure out that whether the applied stress is sufficient for the material so that it can survive, or whether this will fracture at the point of service. So, K1C given is 55 MPa root meter. Okay. So, now there are different ways by which we can solve this problem. Firstly, we can either solve the required fracture strength or the critical crack length that can sustain, or the critical value of K which could be lower or higher than the existing or the given fracture toughness value at this condition of sigma A and A that is given, right. So, let us do this to make it more clear. So, let us say condition 1, when we need to figure out sigma F value. Okay. So, let us simply plug this relation. We knew that K1C equals to y sigma root over pi A. Okay. So, K1C is given as 55 MPa root meter, y we know that this is 1.12. We need to find out that the stress which could be the fracture strength of the material. Okay. And we are considering the A value as the critical value, as if fracture occurs at this condition. This is the critical length that can lead to fracture. So, what is the requirement of stress at that at such condition? So, let us say pi into 0.5 into 10 to the power of minus 3. So, if we solve this, let us see what it gives. So, 0.5 into 10 to the power of minus 3 into pi and root over of that into 1.12. So, that leads us to 0.044 into sigma F, and that leads to sigma F equals to 55 divided by this term, which is 1239 MPa. Okay. Now, this value is greater than the applied stress, which means that the applied stress, that the stress that we are applying is less than the fracture strength that is required for fracture to happen. Obviously, the material is going to survive under such condition. Now, this is one of the way by which we can solve this. The second way, as I said, is by finding out the critical crack length. Okay. So, similarly, we use the same relation, but in this case, we can use the value of sigma A as sigma F. We are considering that the applied stress is sufficient for the fracture to occur, and we need to find out the value of AC. Okay. So, y will be 1.12 once again. So, that makes it okay 1985 0.1 into root over AC, that is equivalent to 55. So, that makes root AC as 0.02 and AC will be something like 7.67 into 10 to the power of minus 4, or we can say that this is 0.77 millimeter. Okay. Now, the applied existing crack length is only 0.5 millimeter. So, that makes that this is greater than A, given A. Of course, that means that if we have a crack of 0.7 millimeter and if we are applying a stress of 1000 MPa, only then fracture can happen. Since the crack length is less than this value, so this means that fracture will not materialize under such condition. Okay, so this also gives us the same understanding that it will survive. And thirdly, we can also solve the value of K1C. Okay. At this condition, when we are applying a stress of 1000 MPa and crack length of 0.5 millimeter, let us say what is the value of K. So, K equals to, in this case, will be given by 1.12 into 1000 into root over pi into 0.5 into 10 to the power of minus 3 whole under root. So, that will be something like this. This comes to 44.39 MPa root meter. Okay. So, this value of K is obviously less than K1C, that is specified here 55 MPa root meter. So, of course, there will be no fracture once again, or it will survive the condition. Okay. Either of these methods are correct and you can use anything for your convenience, but I just wanted to specify the different ways that by which we can use this, and of course, depending on the service condition, we often need to solve it accordingly. So, that in some cases we need to figure out the maximum stress level or the maximum crack length that can be sustained, or maybe the critical value of K. Okay. Now, moving on, now that we have seen the importance of Y on the fracture toughness of the material or the estimation of K actually. Now, fracture toughness of a material under certain condition is a fixed value, right. So, it is a constant value, and if that value of K is achieved, there will be fracture, as simple as that, and this is valid only under certain condition known as the plane strain condition. We will discuss in details in the next lectures. But for now, we all know that fracture toughness is a certain constant value that needs to be achieved, okay, for fracture to happen. Now, when we are figuring out the fracture toughness of a material in the lab scale, like when we are testing the material, we need to select the kind of machine that will be used, the kind of specimen that will be used. Okay, so the typical way, the specimen that we use for fracture toughness testing is known as the compact tension specimen or CT specimen. So, this is as per the ASTM standard, American Society for Testing of Materials standard, that a CT specimen is designed, and you can see all the dimensions are dependent or related to one another. Particularly A and W are fixed, and then the thickness is as per this relation, and the distance between these holes. These holes are used for loading it through pins, and stresses are applied like this. Okay. Now, there are some advantages of using this kind of specimen dimension. The major advantage is that it, so this is a edge crack. So, this is an edge crack, and for this A, the total length of the A is something like almost like 0.5 W, okay, 0.45 to 0.55 to be very specific. This is like this. So, that means half of the width is the crack length. Of course, this violates the basic concepts by which we can determine y equals to 1.12 for edge crack. Rather, y increases to a much higher value, which is around 4 to 5. Not only that, the application of load from this pin positions here, so just at the wake of the crack, that is also advantageous in the sense that fracture can happen much early. So, the main advantage of using this in the lab scale testing is that we can still achieve fracture very quickly. So, that means at a lower load. Okay. Of course, the typical value or the critical value of K at which fracture will happen, that is a constant value. So, that is not going to change, but the load content that is necessary to reach that value is much less. So, the advantage of this is that in lab scale testing, then we can use a much lower load capacity machine that can consume lesser electricity, will make it less expensive. Specimen material wise also it will require less amount of material, so that will conserve the total amount of material, and we can do much more number of tests to verify that. Okay, so that is particularly the reason that we use the compact tension specimen for lab scale fracture toughness testing, so that we can achieve the K1C condition with lower load or the stress condition, so that we can use low load capacity machines. Okay. So, with this, the concept of linear elastic fracture mechanics are considered as follows. So, first of all, it is assumed that cracks are inherently present in a material or a component. Okay, it could be any form of defect that can lead to fracture, and we should consider all the calculations based on this assumption that crack is present in a material. Now, what is crack? Crack is nothing but an internal free surface. So, this is a free surface formed by the breakage of the bond, and that is present in a linear elastic stress field. So, whatever stress we are applying, that is converted to strain as per the very basic linear elastic model, and it follows that, so that we can use this for the calculations. Also, another important parameter for linear elastic fracture mechanics is that the growth of the crack is unstable, okay, which means that once the crack starts growing, it hardly takes any time to lead to fracture. So, let us say we have a compact tension specimen as we have seen. So, once the crack starts growing, okay, there is already a notch here, this notch is machined. Okay, we can determine the length, the tip radius, etc. But once this notch starts growing, then it will immediately lead to fracture. So, this pattern of growing is known as the unstable growth, because everything is according to the linear elastic model, which means that it fractures as per the brittle concept. Okay. This is another thing which is very important for the case of fracture mechanics. Here, when we say something is plastic, means there is a permanent deformation. When something is elastic, that means that it is like a brittle one. Okay. So, this unstable growth of the crack is controlled by the stress intensity factor. We have seen that K value, and K depends on the applied stress, crack length, crack opening mode, whether it is mode 1 or not, and the geometry of the specimen. So, basically K is given by y sigma root over pi a. So, that is how the entire concept of linear elastic fracture mechanics stands upon. Now, coming to the concept of plane stress versus plane strain condition, what we need to see is that even if for the component of similar pattern, if we have different thickness. Now, so far even for the Griffith criterion, we have not talked much about the thickness. We have mentioned that the width or the length of the specimen or the component is infinite, but there is a finite thickness. Why? Because this thickness has a very important or very big role to play to control the fracture toughness of a material or the critical value of K for fracture. In case of thin plate, what happens is that whenever we are applying stress, let us say we are applying stress along this direction, along the direction of y, and the crack is growing along the direction of x. Okay, so this is the loading direction and x is the crack growth direction. Okay, of course, the crack is growing perpendicular to the loading direction. Now, at any point as we are applying the load is supposed to dissociate to x and z direction also, right. So, even if we are applying the stress along y, this is dissociating into sigma x and sigma z counterpart. And for each of these stress values, we are getting the corresponding strain values also. Since we are applying the stress along the y direction, there will be a positive epsilon y. Okay. Strain along the x direction will be counterbalanced by the growth of the crack, but the strain along the z1 is the critical one. But for each condition, we are getting the strain also which are getting dissociated in the perpendicular direction. If we are getting a positive strain along the y direction, then there will be a negative counterparts of strain along the x and z direction to conserve the volume, to maintain the constant volume condition. Okay. So, for each of this condition, we can determine the plus values, the positive values of strains and the negative values for x and z. As I said, for x, this is the direction for the crack growth. So, this will be counterbalanced there, but it is the z1 which is important. Now, for the case of thin plate, okay, if we have a very thin plate, actually the stress along the z direction sigma z is nothing but 0. Okay. So, that makes the stress acting only along the 2 direction. On the other hand, strain is triaxial in that case, because strains are not 0. We are getting this epsilon z component from the other parts of stress also, other counterparts of stress. So, that makes it a condition when we have stress as biaxial, but strain as triaxial. On the other hand, if we are having a thick plate, at that circumstances sigma z cannot be considered as 0. So, sigma z has a finite value, but on the other hand, since we are generating plus epsilon z and minus epsilon z from the different counterparts of stress, those will get nullified and finally we end up having epsilon z equals to 0. So, that leads to biaxial strain in that case. Okay. So, we have biaxial strain for the case of thick plate and we have biaxial stress for the case of thin plate, and based on this biaxial thing, it is named as plane stress or plane strain. Okay. Since biaxial means that it is acting along a plane, right, along 2 directions, that is why this is known as plane stress. On the other hand, strain is acting along 2 direction x and y, and that is why this is known as plane strain. So, eventually what we mean is, for the case of thin plate, plane stress condition is valid, which leads to biaxial stress but triaxial strain. On the other hand, for the case of thick plate, we have triaxial stress but biaxial strain, and that leads to plane strain. Okay. We will look into more details of this plane stress and plane strain concept, but for now we can see that the Griffith criterion can also be modified, and the sigma value that we have generated is particularly for the plane stress condition. On the other hand, for the plane strain condition, since we have the stress also acting along the z direction, we have to take care of this Poisson's ratio term. So, there will be compression on the perpendicular direction. So, that leads to the importance of Poisson's ratio to be considered while calculating the fracture strength of the material. So, this to this Griffith criterion, in the denominator we have to add this root 1 minus nu square. For the case of metallic systems, usually nu or the value of Poisson's ratio is something like around 0.33 for metallic system, and this could have different values. So, for metallic system there is not much of a change, and we can calculate these values under plane stress and plane strain conditions. So, the conclusion for this lecture is that the stress intensity factor includes both the geometrical factors and stress level. On the other hand, stress concentration factor relies only on the geometrical factors. Linear elastic fracture mechanics is based on the primary assumption that material is isotropic, it behaves same along all the directions, and it is linear elastic, which means the stress and strain are followed by this elastic relation, and based on this theory of elasticity, the stress field is calculated. Compact tension, we have seen that such kind of specimens are favored for laboratory testing because we require less amount of stress to achieve the same value of fracture toughness. And in case of plane strain condition, we need to remember or understand that the strain in this case is biaxial, that is why this is termed as plane strain. On the other hand, stress is triaxial. On the other hand, in case of plane stress condition, the stress is biaxial, whereas the strain is triaxial. So, these are some of the references used in this lecture, and I hope you have learned something new in this lecture. Thank you very much.